I want you to imagine a library, but not a normal quiet library. Imagine a library where a tornado has just ripped through the building.
Oh, wow.
Yeah. Every single book has been torn apart, and every single word from every single page has been dumped into this massive, chaotic pile right in the center of the room.
I mean, that sounds like an absolute nightmare for a librarian.
It really is. But here's the challenge for you. If I ask you to reach into that pile and find me a specific story, you just can't do it.
All right, because everything is disconnected.
Exactly. You have all the ingredients. You have Harry, you have Potter, wand, magic. But without the order, without the actual sequence, you don't have a story anymore. You just have a soup.
A bag of words, as we call it in the industry.
Right, a bag of words. And this is really the fundamental existential crisis of modern AI.
Yeah.
How does a machine, which effectively sees that massive pile of words all at once, understand that man bites dog is front page news, but dog bites man is just the standard Tuesday?
It's the problem of position, and honestly, it is much, much harder to solve than most people realize.
Which is exactly what we are unpacking today. We are doing a deep dive into a paper that proposes a solution so elegant, it honestly feels less like computer code and more like pure geometry. We are talking about RoFormer and its secret weapon, RoPE.
Yeah, RoPE, R-O-P-E, which stands for Rotary Position Embedding.
The paper we are looking at is titled RoFormer, Enhanced Transformer with Rotary Position Embedding, by Jinlin Su and the team at Zui Technology. And our mission today is to understand how spinning a word around in a circle, literally rotating it, might just be the key to building AIs that can read entire books without getting confused or, running out of memory.
It's a really fascinating pivot pun, fully intended there, from how we used to handle language.
So let's set the stage a bit. We know language is all about order. If I scramble the words in a sentence, the meaning completely evaporates. How have we been teaching this concept of order to computers up until now?
Well, to really appreciate the solution, you have to understand why the current standard architecture, the transformer, is actually kind of dumb about this specific thing.
Dumb. But I mean, transformers are the state of the art. That's literally what ChatGPT and all the big models are built on.
They are brilliant at capturing context, meaning they know exactly how words relate to each other semantically, but they are terrible at sequence. If you go back to the old days, to recurrent neural networks or RNNs.
Those were the ancestors of the current AI boom, right?
Right. RNNs read text exactly like you and I do. They read word 1, processed it, then moved to word 2, then word 3.
So the order was just baked into the process. You couldn't physically get to the end of the sentence without passing through the middle first.
Exactly. Time step t always happened after time step t-1. The sequence was intrinsic to the hardware operation, but there is a huge problem with that approach.
Which was?
It's incredibly slow. You can't parallelize it.
Oh, because if I have a massive supercomputer with 1,000 processors, 999 of them are just sitting idle, waiting for the first word to be finished.
Precisely. You can't throw 1,000 GPUs at an RNN effectively because you are entirely bottlenecked by the sequence itself. So, enter the transformer. The transformer changed everything because it looks at the whole sentence or even the whole document all at once. It swallows the data in one giant gulp.
Which is great for speed?
It's amazing for speed. It's the only reason we can train models on the entire internet. But it comes with a massive cost. By default, a raw transformer is entirely position agnostic.
So it's back to the library tornado.
Exactly. To a raw transformer, the sentence man bites dog and dog bites man look completely identical because they contain the exact same set of tokens. It just sees man, dog, and bites floating in a void. It has absolutely no idea who did what to whom.
So it's just a cloud of concepts.
Correct. So researchers had to figure out a way to artificially glue the concept of order back onto the words before feeding them into the transformer. And we call this position embedding.
And this is where the Reformer paper kind of breaks down the history, right? Because there have been two main ways to do this before RoPE came along.
Right. The first method is called absolute position embedding. This is actually what the original transformer paper used back in 2017.
How does that work? Is it like assigning a seat number to each word?
That is a perfect analogy. Imagine a theater. You have a ticket for the word man. We staple a literal number to it that says seat 1. We take the word bites and staple seat 2 to it.
So mathematically, we are adding a tag to the word vector that basically screams, hey, I am the first word.
Yes. You have a dense vector of numbers representing the semantic meaning of man, and you literally add another vector of numbers representing position 1 to it.
Okay, that seems simple enough. What is the second way?
The second way is relative position embedding. This one is a bit more sophisticated. Instead of saying you are at seat 5, it focuses entirely on the distance between the words. It effectively says word A is 3 spots to the left of word B.
That feels a lot more natural for language, honestly. Like, if I'm reading a sentence, I really only care that the adjective is right next to the noun it describes. I don't really care that the noun happens to be the 45th word in the chapter.
Exactly. Relative positioning is generally much more powerful for understanding syntax, grammar, and local context. It captures the fluid structure of language much better. But here is the major snag, and this is really the core problem the ZWE team highlights in this paper.
What's the snag?
Almost all of these previous methods, whether they are absolute or relative, involve adding this position information directly to the word's context representation.
Okay, let's unpack that. Why is adding a problem?
Think about it like mixing paint. You have a bucket of bright blue paint, which represents the pure meaning of the word. To add the position information, you pour in a little bit of red paint. Now you have purple. You have successfully encoded the position, but you've slightly muddied the original color.
You're distorting the semantic data just to save the order.
In a way, yes. But mechanically, the paper argues that this additive approach makes these models incompatible with some of the newer, faster architectures we desperately need right now, specifically something called linear self-attention.
I want to pin that term for a second. Linear attention. We hear this buzzword thrown around a lot in AI optimization circles. Why does the additive method break it?
Without getting too deeply bogged down in the calculus, standard self-attention in a transformer is what we call quadratic.
Meaning what exactly?
Meaning if you double the length of the document you want the AI to read, the amount of work the computer has to do doesn't just double, it quadruples. If you triple the length of the text, the computational work goes up 9 times. It creates a massive hard ceiling on how much text an AI can process at once.
Which is why, for a long time, we had that strict 512-word limit on a lot of early models. You couldn't just feed an entire textbook into the prompt because the compute cost would literally explode.
Right. And linear attention is the holy grail to fix that. It tries to make that computational cost grow in a straight line, linear. So double the text, double the work, 10 times the text, 10 times the work. It is so much more manageable, but the math required to perform that linear shortcut is incredibly fragile.
Fragile in what way?
If you use the old additive position embeddings, mixing that red paint into the blue, you fundamentally change the magnitude or the geometric length of the vectors. And changing that magnitude breaks the linear attention approximation. The math just falls apart. The shortcut stops working.
So the industry was basically stuck.
Oh.
We could either have smart models that knew the order of words using additive methods, or we could have fast models using linear attention. But we couldn't have both?
That was the ultimate bottleneck. Until RoPE.
Okay, take us to the aha moment. What does Reformer do differently?
The researchers at ZWE Technology looked at this exact problem and basically said, stop adding, start rotating.
This is where I really need you to visualize this for us. How does spinning a word tell me where it is?
Let's go back to our vector, our arrow on a mathematical graph. Imagine the word king is an arrow starting at the center of the graph and pointing out toward 2 o'clock.
Okay, I've got the arrow in my head.
In the old additive system, to say king is at position 1, we might make the arrow physically longer or shift its starting point on the grid. RoPE says, no, keep the arrow the exact same length. Do not touch the length, just rotate it.
Rotate it how much?
By an angle that directly corresponds to its position in the sentence. Let's say, just for the sake of a simple example, we rotate it 10 degrees per position. So if king is the first word, you rotate the arrow 10 degrees. If it's the second word, you rotate it 20 degrees. Third word, 30 degrees.
That sounds surprisingly simple. I'm literally just winding the word up like the hand on a clock.
It is remarkably simple conceptually, but the mathematical implications are profound. This relies on Euler's formula and complex numbers, but geometrically, here is the real magic trick. When the AI goes to compare 2 words, let's say a word at position 10 and a word at position 20, it calculates something called the inner product.
Which is basically the AI checking how strongly related those 2 words are to each other.
Right, and when you do that specific math with these rotated vectors, the absolute positions naturally cancel out of the equation entirely. The only thing left mathematically is the difference between the angles.
Wait, walk me through that step by step.
Okay. If my arrow is rotated to 100 degrees, and your arrow is rotated to 110 degrees, what is the difference?
10 degrees.
Right. Now, imagine we take that exact same phrase and shift it way down the page. Now, I'm at position 200, so my arrow is rotated to 200 degrees, and you are at position 210. What is the difference now?
It's still just 10 degrees.
Exactly. The relative geometric relationship between the two words stays completely locked, no matter where they appear in the massive block of text. You have encoded the absolute position by rotating it a specific amount from 0, but the model naturally perceives the relative position, which is just the distance between the two hands on the clock.
That is incredibly slick. You're getting the absolute best of both worlds.
Yeah.
You get absolute addressing and relative dependency purely through continuous geometry.
And, crucially, you didn't have to add anything to the magnitude.
You didn't muddy the paint color.
Correct. You changed the direction the arrow is pointing, but the magnitude, the physical length and intensity of the vector stays exactly the same. That is the whole key. Because the magnitude is perfectly preserved, this rotational method is entirely mathematically compatible with those fast linear attention models we talked about earlier.
So we finally have a way to tell the AI the exact order of the words that doesn't break the speed limit of the hardware.
That is the big promise of RoPE, but it actually gets even better than that. There are some side effects of this rotation approach that turn out to be incredibly useful for how natural language actually works in the real world.
Side effects like what?
Think about how you read a long book. If I say a word right now, it is very strongly related to the word I said 1 second ago. It's somewhat related to the word I said 10 seconds ago, but is it strongly related to a word I said 10 minutes ago?
Probably not. The context naturally decays. If you are talking about apples right now, the fact that you mentioned a sports car 10 pages ago probably doesn't matter to the current sentence.
Exactly. We call this long-term decay. In natural language, local context matters the most. Now, in the old additive systems, you had to kind of just hope the model naturally learned this decay, or you had to hard code a bias into the system to force it. But with RoPE, the decay happens naturally.
Why does rotation cause decay?
Because as the difference in angles gets bigger meaning as the words get further and further apart in the sentence, the inner product between their vectors naturally gets smaller. The math effectively says, hey, these two words are really far apart in rotation space, so they're pointing in wildly different directions. Pay less attention to their connection.
That is fascinating. So the pure geometry of the vector space naturally mimics the way human attention works when reading.
It does. It is an intrinsic property of the rotation itself. You get decaying intertoken dependency entirely for free. You don't have to spend compute training the model to do it. It just falls right out of the math.
That feels almost too elegant. And I have to admit, I'm always a little skeptical of things that sound perfect on a whiteboard. Does this actually work in practice? Or is this just beautiful math that fails when you throw messy real-world data at it?
That is absolutely the right question to ask. The Zui team didn't just write out the equations and call it a day. They ran a rigorous gauntlet of benchmarks. They built a model called RoFormer, which is essentially a standard transformer with RoPE swapped in, and put it up against the industry heavyweights.
Who did they fight first?
First up was machine translation. They used the WMT 2014 English to German task. It is a very classic standard test for translation accuracy in the field.
And how did the scores look?
The baseline transformer, the standard model without RoPE, got a BLEU score of 27.3. RoFormer got 27.5.
Okay, I have to be brutally honest here. That is an improvement of 0.2. That doesn't exactly sound like a revolution. That sounds like a statistical rounding error.
Well, in the ultra-competitive world of NLP benchmarks, a 0.2 bump is actually statistically significant. But you are totally right. It is not earth-shattering on its own. If that translation score were the only result in the paper, we probably wouldn't be doing a whole deep dive on it today.
So where is the real, undeniable win for RoFormer?
Efficiency. They took the BERT model, which is one of the most popular and foundational architectures in the world, and they pre-trained it from scratch using RoPE instead of standard embeddings. They found that RoFormer converged significantly faster than standard BERT.
Define converged faster for the listeners who maybe aren't training massive neural networks in their basements.
It basically means the model learned the material in fewer training steps. When you train an AI, you track something called a loss curve, which essentially measures how many mistakes the model is making over time. With RoPE, that loss curve dropped much steeper and much earlier in the process.
So if I am a tech company renting a supercomputer by the hour to train my next model, RoFormer literally saves me time and money.
Potentially a massive amount of money. In an era where training a top-tier frontier model costs tens of millions of dollars in electricity and hardware time, learning faster is a colossal competitive advantage.
Okay, that definitely puts the zero point 0.2 score in context. It got a slightly better translation score, but it got to that level of intelligence with far less sweat.
Exactly. And they didn't stop there. They also ran it on the GLUE benchmark, which is kind of like the decathlon for AI reasoning. RoFormer beat BERT on 3 out of the 6 distinct tasks they tested, specifically on tasks involving checking if two different sentences mean the exact same thing.
Which brings us right back to that rotational property preserving the relationships. If it maps distance so perfectly, it's naturally going to be good at comparing the structure of things.
Right. But the experiment that really sold me personally, the one that proves the fundamental theory, was the one involving Performer.
Performer is one of those linear attention models you mentioned earlier, the really fast ones.
Yes. Remember, we said the old additive embeddings broke the math for linear attention. So theoretically, RoPE should fix it. They took RoPE and plugged it directly into Performer. And the loss curve dropped dramatically compared to a standard Performer without it. It definitively proved the compatibility.
So it actually unlocks that massive speed upgrade we were promised.
It does. But there is one final boss battle in this paper, and this one is specifically targeted at the problem of length.
Because if you were just rotating a vector, theoretically, you can keep rotating forever. You don't just run out of numbers the way you might run out of distinct position tags.
That is the theory. And to test if it held up, they used a very specific Chinese dataset called CAA 2019 SCM.
That sounds like a legal data set.
It is. It stands for Chinese AI and Law. The task is to look at 3 separate legal cases from the Supreme People's Court and figure out which 2 are the most similar based entirely on the raw fact descriptions.
And legal cases are not exactly short tweets. They are incredibly dense, and very long. The standard BERT limit, as we discussed, is usually 512 tokens. But most of these court documents are significantly longer than that.
So how did the models handle the extra length?
First, they tested them at the standard capped length of 512 tokens. At that length, RoFormer performed about the same as other optimized Chinese models like Wobert. It was basically a tie game.
Okay, fair enough.
But then they stretched the input window. They pushed the sequence length all the way to 1,024 tokens.
Doubling the cognitive workload on the model.
And this is exactly where the old additive methods usually choke. The model just gets lost in the noise because the position information isn't crisp enough at that distance. The red paint has completely overwhelmed the blue paint. But RoFormer, it didn't just survive, it actually improved. It beat Wobert by an absolute margin of 1.5%.
Now, 1.5% is a much, much bigger number than the 0.2% we saw in translation. In a complex classification task like matching legal documents, a 1.5% jump is a dominant lead. It essentially proves that as the text gets longer and more complex, the advantage of RoPE gets significantly bigger. The rotation keeps the position information mathematically clean even when you are 1,000 words deep into a document.
That perfectly validates the intuitive argument you made earlier.
Yeah.
If I'm using post-it notes, the additive method, eventually my desk is just completely covered in them and I can't see the actual desk anymore. But if I'm using rotation, I can just keep spinning the dial indefinitely.
That is a really great analogy. The geometric distinction remains sharp even at extreme distances.
I want to zoom out a bit here as we wrap up. We've talked extensively with the math, the vectors, and the benchmarks. But what does this actually mean for the person listening who just wants to know where AI is going? Why does RoPE matter to the future of the technology?
It represents a fundamental shift in how we design the basic architecture of these digital brains. For a long time, we were just throwing brute force data at the wall. We were essentially saying, here is position 1, here is position 2, and forcing the machine to memorize it.
And RoFormer is doing something different.
RoFormer is elegant. It suggests that the absolute best way to represent human language inside a computer isn't just discrete lists of numbers, but continuous geometric relationships. It treats the concept of order as a fluid motion, a rotation in space, rather than a clunky, discrete step.
It feels a lot more organic.
It really does, and practically speaking, it kicks the door wide open to that linear attention future where context windows might become effectively infinite. If the math remains stable, why stop at 1,000 tokens? Why not 10,000? Why not feed the model the entire Library of Congress in one single prompt?
That is the ultimate dream for AI right now. But here's the part that I actually found most delightful in reading the paper. For all of this success, for all of this empirical proof, The authors actually make a pretty huge confession right in the text.
Oh, yes, they do.
They completely admit that they don't entirely know why it converges so fast during training.
Right. They have all the math for the rotation perfectly locked down. They can prove the relative position property on a whiteboard all day long, but the empirical observable fact that it learns the data faster, they say, and I quote directly from the paper, "We have not come up with a faithful explanation."
I find that somewhat reassuring, but also slightly terrifying. We built a much better engine. It objectively goes faster on the track, but we aren't 100% sure why the fuel mixture is so potent.
It is the classic black box problem in deep learning. Sometimes the experimental results just outpace the underlying theory. But honestly, that's how science works. You observe a powerful phenomenon, you harness it to build better tools, and then you spend the next 5 years trying to figure out the exact why. It leaves a fantastic mystery for the next generation of researchers to solve.
So let's distill the core takeaways for you listening today. Number 1. The bag of words problem is solved not by awkwardly stamping numbers onto words, but by spinning their mathematical vectors in space.
Number 2. This multiplicative approach, RoPE, allows us to cleanly decouple the position of a word from its underlying meaning. It gives us vastly cleaner data and keeps the vector magnitude stable, which is the absolute key to unlocking those faster linear attention models.
And number 3. It naturally mimics the human brain's tendency to focus on local context while still keeping track of the long game, performing better and better as the documents get thicker and more complex.
I couldn't have summarized it better myself. It really is a triumph of applying geometric intuition to a data problem.
It really makes you wonder about something bigger. If human language, with all its messy poetry and strict grammar, can be mapped so perfectly to physical rotation, if the difference between man and dog is ultimately just an angle in a high-dimensional space.
Where are you going with this?
Well, we know that human spatial memory, like how we navigate a city, uses grid cells in the brain to map physical geometry. And cognitive scientists are starting to think we use those exact same grid cells to map abstract concepts. So if RoPE is using physical geometry to map language, are we just engineering a neat math trick, or are we accidentally discovering the literal geometry of thought itself? Maybe the human brain is just rotating concepts in a biological vector space.
Wow, that is an incredibly heavy thought. If the architecture of artificial intelligence is converging on the biological architecture of mammalian spatial navigation, that changes how we view both the AI and ourselves.
Maybe the difference between man bites dog and dog bites man really is just a matter of perspective, or in this case, literally a matter of degrees.
A 10-degree shift completely changing the headline. I really like that framing.
We will leave you to ponder the geometry of your own thoughts. Thanks for spinning through this deep dive with us today.
See you next time.
Take care.